Solution concentration. We talked on Thursday, we jumped ahead and we talked about how solvent solutions form and how to predict whether things are soluble. So we're kind of going seemingly backwards here. When table salt's mixed with water, it seems to disappear, right? You stir it in there and you don't see it anymore. But if you taste the water, there's definitely something different about the water. It's salty now. It has formed a homogeneous mixture. Homogeneous. It's the same throughout. The salt's still there. You can taste it. If you boil the water away, you'll be left with a salt residue in the container. And we saw that the other day when we had, what was it, zinc iodide that you made? And it was dissolved, and then you heated it and evaporated all the solvent off, and you've got this salt left. Homogeneous mixtures have another name. They're called solutions. They're not compounds, but they're solutions. And they're mixtures because the amounts of different parts can vary. And so we have two terms that we use. Solvent is one component, and solute is the other. You can have only one solvent, and it's generally the one that's present in greater amount. Whatever you have more of, that's considered the solvent. And the solvent does not change state. If it was a liquid, it stays a liquid. The solute is present in lesser amount. The solute may change state. You can dissolve a solid in a liquid. It's no longer a solid. It becomes part of the liquid. And you can have more than one solute. Some solutions have lots of different solutes. So solute, solvent. The composition can vary. That's why it's a mixture. Pure substances have constant composition. They're always the same. But mixtures can vary. Even if you take ocean water from different parts of the ocean, or if you come up the delta to the river, you see that the salt concentration changes. It's still a solution, but the components of the mixture are in different amounts. And so when we describe solutions, we have to say something about how much of the solute is there. We can't just give it a single name like we can with a compound or an element. So we have qualitative descriptions for solutions. These are relative, they're non-numerical. We have the words dilute and concentrated, and they are just relative terms. So dilute is a small amount of solute, and a concentrated solution is a large amount of solute. So if we look at these two flasks, and if these are representing the solute molecules, we could say that this one is dilute and that one is concentrated, because there's more. Qualitative descriptions are only a little bit useful, really quantitative descriptions. And the one that chemists use a lot is called molarity. Molarity, and it has the symbol capital M. This is defined as the amount of solute in moles divided by the volume of liter in solution. And these units are always the same. It's moles of solute per liter of solution. If we see this unit, we might have a 12 molar solution. That means 12 moles per liter. Capital M means moles per liter. Here's an illustration of how you might make a 1 molar sodium chloride solution. 1 mole per liter. So in a 1 liter solution, you're going to have 1 mole of sodium chloride. You're going to have to calculate the mass of that, because the balances don't weigh things in moles. They weigh in mass. So you have to calculate the mass. And for making solutions where we want to have a fairly accurate concentration, we use volumetric flasks, because we can measure the volume more precisely that way. And so you're going to put the solid in there, It's a little deceptive. I would actually put some water. I would have solvent in here first and then add the solid. And you need to mix this until it's all dissolved. Because once you start filling up this neck, it's very hard to mix. My husband did a cool demonstration, and I think I'll try to do that for you in lab, of how poorly it mixes once you get up in here. The reason these have such a tall neck, and they've got an etched line here at the volume, so this is probably a 1 liter volumetric flask, and there's a line here. With the tall, skinny neck, a small change in volume is seen as a relatively large change in height. If you try to measure something in a very shallow dish, you can't see much of a change in height, but because the neck is narrow, you can get a more accurate measurement. So you add water just to the line so that the volume of the whole solution, the solvent and the solute, is this volume. Then you put the stopper on it and you have to invert it. I think it's like 20 times to get it to thoroughly mix. Well, molarity is very useful, and we use it in a lot of calculations. It works out to be a great conversion factor between moles of the solute and liters of the solution. So 0.5 molar sodium chloride has 0.500 moles of sodium chloride for every liter of solution. So we can use that to convert liters of solution to moles of sodium chloride, or moles of sodium chloride to liters of solution. And hopefully you've seen this stuff before too. How many grams of solute are in 1.75 liters of 0.460 molar sodium hydrogen phosphate? Well, let's pull the numbers out. We've got 1.75 liters, and we've got 0.460. The capital M is great. And by the way, when I write it, well, I'll just do it here. When I write it, because I don't want to take the time to make my capital M super pointy, you know, if I just go over here, is that a capital M or a lowercase m? Kind of hard to tell, right? It's relative. Or who knows? So a convention that many chemists use is we underline it if it's a capital M. So that's capital M. That's useful. It's easy to type, but students often get confused when they try to do calculations because they forget that it's moles per liter. You're writing with a pencil or a pen. Write it like this so it's obvious that it's moles per liter. This is a conversion factor. This is not. Even if we didn't read the problem, if we just looked at the numbers and the units, we could calculate something and we'd be halfway there to what they're actually asking us for. They want to know grams of solute. Well, we've got these two numbers. This one has regular units. This is per. This is the conversion factor. So from liters, we can find moles of solute. But they want grams of solute, right? But we've learned how to do that. We can take moles and go to grams. We need the molar mass. What do we need before we can find the molar mass? The chemical formula? They gave us the name. They like to do that to you in 1A. Sodium hydrogen phosphate. Remember what hydrogen phosphate is? Do you remember what phosphate is? PO4 3-. So that's phosphate. Hydrogen phosphate has a hydrogen ion on it. So it's got an H plus added over here. And so that changes the charge to 2-. So that's hydrogen phosphate. And sodium has what charge? +1. So if we put those two together, we're going to get Na2HPO4 is our formula. And we'll use that to calculate the molar mass. So I'm going to do that up at the top. 2 times the mass of sodium plus hydrogen plus phosphorus plus 4 times the mass of oxygen. $141.958. That would be grams. So the molar mass is what we need to go from moles to grams, and the molarity is what we need to go from liters to moles. So we start over here with 1.75 liters. We're going to multiply by moles and divide by liters, so the liters cancel out. We're going to multiply by grams and divide by moles, so the moles cancel out. Isn't that cool? I love that. It's just, the units, it just does that all by itself. It's awesome. And then we stick the numbers in. So 0.460 with the moles. 0.460 moles. And then this number, 141, goes with grams. 0.958 per 1 mole. And our answer should have 3 significant figures because the 1.75 and the 0.460 both had 3 sig figs, so this will be 114 grams of sodium hydrogen phosphate. Any questions? There's like almost an infinite number of questions that could be asked, right? So you don't want to have to memorize how to do every stinking kind of problem. You want to understand the units, how to put them together and manipulate them. Remember what capital M means. It's moles per liter. And you just pull these things together. You'll often have to look at a periodic table and calculate a molar mass. That's why we just do not do chemistry without a periodic table. There's one on the wall for an exam. I give you your own copy so you don't have to crane your neck looking at the wall. We often make concentrated solutions and store them in the stockroom. And we call them stock solutions. They're stored in the stockroom. They're stock solutions. And then, when we need a more dilute solution, we take those and we add solvent to them and dilute them. It's a little bit like going to the grocery store and buying concentrated frozen orange juice. Why do we store it concentrated? It takes up a lot less space, right? Can you imagine a freezer full of jugs of frozen orange juice? It would take up so much space. They take a lot of the water out, and then there are these nice little cans that are easier to transport. So when we do this, we're diluting a solution, much like you do when you take that can of orange juice and you add water to it so that you can actually drink it. You take the can of frozen orange juice and you pour it into a pitcher, and then you fill the can with 3 cans of water and dump it in there. You mix it up. What you have has changed in volume, but all the orange goodness that was in the little can is now in the big pitcher. You haven't lost any of that orange goodness, right? You haven't gained any either. The amount of solute doesn't change when you dilute a solution. Only the amount of solvent changes. So the volume of the solution changes, but the amount of solute stays the same. And if you're interested, I can show you why this is true, but most students aren't all that interested. This is the equation that we use to calculate dilutions. The molarity of the first solution times the volume of the first solution is equal to the molarity of the second solution times the volume of the second solution. M1V1 equals M2V2. Good thing to remember. So here's an illustration of diluting a solution. Here they're taking 0.150 liters of a 10 molar stock solution and putting it into this volumetric flask. How many moles of solute are in that? .15 liters times 10 mole per liter gives us 1.50 moles of solute, right? So we're putting that much solute in here from that solution, and then we're going to add water until the volume is now 3 liters. So we've got this much solute now in 3 liters of solution. So if we take that 1.50 moles and divide by 3.00 liters, we get 0.500, right? Oh, let's just go on the next line because it's all cramped up. That's what this equation is doing. The molarity of the first solution times the volume of the second solution is equal to the molarity of the second solution times the volume of the second solution. If you know 3 of them, you can calculate the 4th. Let's do one. Isotonic saline is 0.15 molar aqueous NaCl. It simulates the total concentration of ions in many cellular fluids, and its uses range from cleaning contact lenses to washing red blood cells. Okay, that middle part was all fluffy stuff. How would you prepare 0.80 liters of isotonic saline from a 5.0 molar stock solution? So we've got this number, and this number, and this number. So we've got 0.15 moles per liter, and we've got 0.80 liters, and we have 5.0 moles per liter. We're going to take the stock solution and dilute it. This is saying we want 0.8 liters of isotonic saline. Up here it says isotonic saline is this. So these two go together. These two are connected. So let's call this the molarity of the first solution, and this will be the volume of the first solution. It doesn't matter if you call it 2 or 1, as long as you get them connected in the right way. Then this is going to be the concentration of the second solution. What can we calculate? We can calculate V2, right? So here we have M1 V1 equals M2 V2. It always reminds me of R2D2. My kids used to say CP30. I don't know why they did that. I don't know why I remember that. We need to solve for V2. Just a quick lesson in algebra here. We're going to divide both sides by M2 to get rid of those. So V2 is M1V1 over M2. Be careful rearranging equations. On that worksheet I just turned back, a bunch of you did some silly things. And I'm pretty sure you know better, but you just got a little sloppy. So V2 is molarity 1, 0.15 moles per liter, times volume 1, 0.80 liters, divided by molarity 2, 5.0 moles per liter. Moles per liter and moles per liter cancel. 0.025? 0.024, yeah. So 0.024 liters. Does that answer the question? What's the question? How would you prepare this solution? 0.024 liters. It doesn't answer the question. You did the hard calculating part, but you're not really done yet. What is this number telling us? This is how much of the stock solution we need to add, and we need to dilute it to 0.8 liters. So, very briefly, dilute 0.024 liters stock solution to 0.8 liters. Very brief, but it tells me that you understand what the idea here is. Okay? Any questions? We can also do stoichiometry involving solutions because the molarity relates moles to liters. Liters is a volume that we can use. And so this is a modified version of our grams to moles to moles to grams. So regular was grams to moles to grams. But we can also have volume. You can start with volume, go to moles to grams. You can start with grams, go to moles to volume. All kinds of different possibilities. A whole world of fun problems. Oh, all the words. So many words. A common antacid contain. Good grief. Okay. Common antacid contains magnesium hydroxide, which reacts with stomach acid to form water and magnesium chloride solution. As a government chemist testing commercial antacids, you use 0.10 molar HCl to simulate the acid concentration in the stomach. How many liters of stomach acid react with a tablet containing 0.1 grams of magnesium hydroxide? We need a chemical equation. Right? We've got magnesium hydroxide. We're told that reacts with stomach acid, forming water and magnesium chloride. We could write an equation for this. So what is the formula for magnesium hydroxide? Oops, that's not what I want. Mg. And what's the charge on magnesium? +2. And hydroxide has what charge? -1. So we're going to need 2 of the OHs. So magnesium hydroxide. And for the stomach acid, we're using HCl. And it says this is forming water and magnesium chloride. It's going to be MgCl2. Because the chloride is -1 and the magnesium's +2. And so that's how we get this formula. And we need to balance the equation. There's 1 magnesium and 1 magnesium. Here's 2 chlorines, so I better put a 2 over here. No, not there. Over here. 2 chlorines and 2 chlorines. Here's 1 oxygen. There's 2 oxygens over there. And then there's 4 hydrogens here. 2 plus 2, 4 hydrogens. Okay, so we're balanced. We need that, and that can help us to organize these numbers that they gave us. 0.10 capital M HCl. So I'm going to write that under the HCl. 0.10 moles per liter. How many liters of stomach acid? I wrote that in the wrong place. Okay, I think that's 8 mistakes today. Good grief. Moles per liter. How many liters of stomach acid? So the question is, how many liters of that to react with a tablet containing 0.1 grams of magnesium hydroxide? 0.10 grams of that. You see how I took these numbers and put them up there under the thing they relate to? So we're given this information, mass of that compound, we're given a concentration here, and we're asked for a volume. This is the one that the question mark pertains to. So this is not the thing we're starting with. It has a number, but we're not going to start with that. We're going to start with grams of magnesium hydroxide. So this time we're going to write the path out. We're going to start with grams of magnesium hydroxide. And we're wanting to end up with liters of HCl. We always have moles to moles in the middle. So this is going to be grams of magnesium hydroxide to moles of magnesium hydroxide to moles of HCl. Can we get from moles of HCl to liters of HCl? Yeah, we've got the molarity. Okay, so 0.10 grams magnesium hydroxide. Got moles magnesium hydroxide per gram magnesium hydroxide. Those units cancel out. Then we've got moles of HCl to moles of magnesium hydroxide. And those units cancel out. Then we've got liters of HCl per mole of HCl. And those units cancel out. Any questions? The middle one's easy. Do that one first. There's a 1 implied in front of the magnesium hydroxide. Some people really want a number in there, so there you go, there's the number. There's a 2 in front of the HCl. Well, there's that. Liters and moles. This is related to the concentration. 0.10 moles per liter. So the 0.10 goes in the bottom. Moles per liter. And then we need the molar mass of magnesium hydroxide. I forget magnesium. 24.31. Plus 2 oxygens, plus 2 hydrogens. $42.326. I feel like saying, can I get an amen? Is that right? This isn't church. Did I do it right? No? No, that doesn't make any sense, does it?
No.
24.31 plus 32 plus 2.016. Yeah. Number 9. How's that? Is that better? I left off an oxygen. Who cares? We do care. We care. 58.326. You need to write stuff down. Have I said that? Yeah. You need to write stuff down. It's really easy to do stupid things like that. And you get the wrong answer. If you didn't write anything down, you have to start all over. If you wrote stuff down, you can go back and look at what you did and realize, oh, that was dumb. Fix that piece. And there we go. We've got the right answer. We type it into Mastering Chemistry, and we're good. 0.1 divided by 58.326. Let's see if I can do this. Times 2 divided by 0.1. Two sig figs. 0.034. Agree or disagree? Yeah, you can't vote if you don't actually have your calculator out. Like, oh, it looks good to me. Yeah. Close only counts in horseshoes and hand grenades. Any questions?